Well, today let's take a look at the Diels-Alder reaction. So just to refresh our memory here, I'll link to our lecture from previous in the semester, but a review from that is that, remember, we have our diene and you have your dienophile. So your diene is up here, it's got the two double bonds, and your dienophile is down here. It's the thing that loves the dienophile. And we can always do these reactions approaching from the bottom side or approaching up from the top side. Right? If we're coming here from this bottom side, right, we form this kind of chair structure that's typically drawn out as this flat structure like this, right? So recall that these two H atoms, as we approach from the bottom, will be pushed into this up position, and then the A and the B here will be pushed in the down position, right? So if you just remember that these guys are always getting pushed up, and that these two groups here pointing in always get pushed down, that'll give you always the correct stereochemistry in your products as you go through and draw them out. Now if we do this from the top side, then we end up with these H's getting pushed down. So from the bottom attack, the H's go up. From the top attack, these H's get pushed down. So there's your two H's here. And then your A and B here will be pushed up. So they're going to be pushed in this up position. And then if we take that molecule and kind of grab it like a plate and rotate it towards us, you end up getting this product. Now these are enantiomers of each other. So often what I tell students is, you whenever possible, enantiomers will form. So if we just take a look at this bottom approach, draw our product and make sure it's not meso or something, then we look at it, and if it's a chiral molecule, we would just draw its enantiomer out. So we don't have to go through the whole rigmarole of drawing out all these intermediates necessarily. Now there's another rule. There's this endo rule. So the endo rule has groups pointing down. So it's in this down position. And the exo position is kind of equatorial. It's coming out. Or the endo position is your axial position. And one of the things that we often do on the dienophile is we put groups on there that are electron withdrawing. And they typically contain carbonyls, for example, aldehydes and ketones and esters and things of that nature. So the reason why this endo position is preferred, even though typically speaking larger substituents like this exo position, is because of the way that the p orbitals overlap and the transition state for the endo approach. So if you recall, we have to have proper alignment of our p orbitals of the diene and the dienophile in order to have a constructive overlap. And also, if we look at this, like if this is your carbonyl, that's like a carbon-oxygen double bond. It's just a double bond, right? It doesn't really matter what it is. We get the secondary p orbital overlap here and back here. Right? So that orbital overlap lowers the transition state energy, which is why this endo position is more favored. Now, the reaction that we're going to look at today is between cyclopentadiene and maleic anhydride. And so if we get our endo approach, we put our maleic anhydride down here in this bottom position. So it's a complicated looking molecule, but we put these substituents pointing down. Right? And the way that we would typically draw that out is we'd rotate it around and we would draw it out so that it looks something kind of like this. So that would be what I would call your bottom approach. Now you can still do this top approach, and when you do the top approach you get this molecule. And if you take that molecule and you rotate it and you kind of make it flat, you get this geometry. But this molecule has a plane of symmetry down the middle, so if we rotate it around and flip it kind of like a page getting turned from the top to the bottom, we end up getting this, and those are the same. So in our reaction, we're going to use either sand or water bath for our heat source of a round bottom flask that has about 0.1 grams of maleic anhydride, about 0.4 mils of ethyl acetate, and 0.1 mils of cyclopentadiene. And we'll connect it to an air condenser and a drying tube, and after the reaction has gone to completion, we'll allow the solution to cool and we'll collect some crystals. So when we collect those crystals, we want to be careful about the rate of temperature decrease. So in this diagram here, we can see a rapid rate of cooling, right? So we see that upon cooling rapidly, we don't allow sufficient time for these little triangle impurities to be excluded from our crystal lattice structure. Now, what that's going to do is that's going to give us a product that has impurities in it, and that will be detected by taking melting points. So recall, those impurities will cause a melting point to be lower, so it lowers it, and it will also broaden the melting point range. Right? On the other hand, if we allow slow cooling, we allow sufficient time for these little triangles to be excluded from the growing crystal lattice structure, and in the end, we end up with larger crystals with fewer impurities trapped inside.